Okay, welcome back to part two of Lenses and Mirrors. I hope you took a little break, had a nice cold Coca-Cola. So we're back to drawing some diagrams now. So now that we have a better idea of the lens, what it looks like, and what kind of lenses, we can now start to think about how do we analyze situations with objects and looking at objects through lenses and mirrors. So first of all, this diagram looks a little confusing. These different colored rays. But when we draw a ray diagram, we first of all only need to draw a few rays because finding images produced by lenses and mirrors is really just about knowing where a few rays intersect. Um, there's three, we call these the principal rays because they're kind of the three rules for easy and they always follow the same exact rules. Principal rays. Typically in the AP exams, they require, I mean, you have to have two, right? Because you need at least two to intersect to show me where the image is. So two of three. Sometimes you can only do two of three, depending on, maybe the size of your drawing. You just can't get the third one in. So let's talk about it. So first of all, this is for a lens, but again, they're very similar. Um, I've got my lens drawn as just a vertical line here. Again, if we have a big, thick drawing of a lens, right? If I were to come in here and draw this lens, it looks something like that. That's really exaggerated curvature for that lens. So I probably don't want that. A vertical line will give you much more accurate results every time. Let's get rid of that. So you notice that I have my focal point on my principal axis, which is always a good place to know. It sometimes is given to you. Sometimes you have to draw it in, right? If you're drawing your own diagrams, you have to create your own scale and you kind of draw it in. Remember, the focal point is the point where all parallel rays would converge to that point. We're actually going to use that rule for two of our three rays. And then you also see we have the center of curvature, or 2F, on there as well. So those are kind of key geographic points where we can identify where the image is. Is it between F and 2F? Is it outside of 2F? Is it between the lens and F, and so on and so forth. So here are the three rules. Number one rule, the blue one. Any parallel ray of light, right? So we start with our image, or I'm sorry, my object, and we keep objects very simple. Arrows. We start at the principal axis and we denote the object by an arrow. Arrows are good to use because they have direction, right? We know where the top is and we know where the bottom is, and it has size. I know how long it is, and it has location. I can put it anywhere on the principal axis. So we always start with the bottom of the object on the principal axis, and then we draw away from the principal axis. We also know right side up and right side down. And you can see on this diagram that I actually get an image that's upside down. So anything below the principal axis is always going to be upside down. The bottom of the object is always on the principal axis. So that means if my rays converge at a point below it, then that's where the top is, and it's upside down. So my blue ray, any ray, and this was the rule for knowing what the focal point is in the first place, any parallel ray to the principal axis always refracts through the focal point, And I'm going to extend this to say that if this was a mirror, then any parallel ray is going to just reflect back through the focal point. Lenses and mirrors are very similar. There's only rule 2 is a little bit different. It's not that it's different, it's just a little more convenient to change the rule for a mirror. Let's skip down to rule number 3 because if any ray parallel goes through F, then that means any ray that goes through F on the real side, or on the left side of the lens, then when it hits the lens and it refracts, it's going to refract through, it's going to refract parallel. So you see how these are just opposite rays of each other? Parallel, through F, parallel. So those are my two. Now I could stop there, right? Because as long as my two rays converge over here, then I know where my image is. But the problem is if you make a mistake with one of the two first rays you draw, you never really know it because two rays will always typically converge somewhere. It's the third ray that's kind of the checker. And the third one, which I have as rule number 2, or principal ray number 2, is the easiest of the three because any ray that passes through the center, and that's why the vertical and the principal axis are important, because any ray that travels right through the center of the lens, regardless of what angle it moves through, will pass straight through without refracting. So that yellow ray goes straight through the lens, and you notice that it just intersects with the other two. So the point either on the right, if my image ends up forming on this side, right, we would call this a real image because it's where the actual rays of light through the lens converge. I can also see that my object is that big and my image is only that big. So it is reduced in size, right? It's smaller. So sometimes lenses and mirrors magnify images. Sometimes they reduce them. I could also see that it is upside down. So another property is that it is inverted. And then the location of that, I can see that the image, the object started out beyond 2f, but my image ends up between f and 2f. So if I put a little screen right there, I would be projecting that image at that particular location. So those are my typically the four things that I would say about an image formed by a lens or mirror. Is it real or virtual? Is it bigger or smaller, or the same, I guess is an option? Is it inverted or right side up or erect is the word that's used usually? And then where is it? Is it between the lens and focal point? Is it between the focal point and center of curvature? Or is it at the center of curvature or beyond the center of curvature? So where is it? So for a mirror, the only rule down here that I would change is that light doesn't go through a mirror, so this yellow ray right here passing through the center of a mirror doesn't really make sense. The actual rule would be that it would bounce off of the mirror at the exact same angle, right? The law of reflection. However, that one's tough too, because then you'd have to measure the angle, really. You wouldn't be able to eyeball that so well. So the third rule that's the easiest for a mirror is that any ray that goes through 2f will bounce straight back through 2f. 2f is the center of curvature, so any ray that goes through the center of a circle will always hit the outside of the circle at 90 degrees, which means it's going to remember law of reflection, it's going to bounce right back at 90 degrees. So that's an easy one to remember from mirrors. But again, 2 out of the 3 rays will normally get you the answer. The third one will just help you check to make sure you've done it correctly. So let's do a couple. I'm going to use, always when you're doing these by hand, you never ever freehand them. You don't have math to fall back on, so the geometry has to be very precise, and we always have to use straight edges, sharp pencils. Luckily, I've got little tools up here, arrow tools. So let's see if we can do this one. This is looks like a mirror, so let's start with the lens. So you see we have an object way over there on the right. It's way outside of 2f. So we have 3 rules that we want to follow, so let's start to draw our rays. So my first ray, remember, is any ray that is traveling parallel to the principal axis is then going to refract through the focal point. We want to extend these rays far enough that we can then, because we don't know where that image is going to form yet. Rule number 2, and let's maybe do a different color on this one, is any ray that goes through the focal point right there is then going to come off of there parallel. Sorry. I wasn't a big fan of where this one ended up, so let's fix that. There we go. And then the last one, rule number 3, should confirm. And again, I've got a big thick lens here, so I made sure I went right through the middle of the lens. And if you need to bisect the lens with a vertical axis, then by all means do, if it makes it easier. Somewhere like right there would be my vertical axis. And then my third ray, let's do a different color here. Let's make this one a nice green. says that if we go straight through the center of the lens right there, then I should not get any refraction. And we can see that all three of my rays then converge at a single point over here. And now look how small it is. So if I'm really far away from my lens, then my image that I get, I can draw it in there, and that's an arrow. If you can't really see it, my image is right there. It starts at the principal axis, and then it goes, the top then is where my three rays meet. So I can see that it is very small, it is reduced, just like we saw in the last one. It is inverted. It is between F and 2F again. And then also we can see that it is real. You need to look up, maybe make sure you understand what real and virtual is. Light rays actually form the image that makes it real. I could project it on a screen. Real image. Okay? And that's actually the same example that we used back here, but now this one's farther away, even beyond 2F. So we can start to see that what happens to rays of light when they're very, very far away? Well, distant, very distant objects, the rays of light will become more and more and more parallel. Light coming all the way from distant stars, for example, by the time they get to our eyes, those few rays that actually make it into our eyes are almost traveling parallel to one another. So we would imagine that as the object goes towards infinity, the image would move towards the focal point because the rays are becoming more and more and more and more parallel. As we move closer and closer to 2F, then the image moves closer and closer to 2F as well. But I'm going to let you then apply these same rules to your other diagrams. Let's do one real quickly for the mirror. We're going to use the same rules. I'm going to go quick this time because this video is getting kind of long. So remember, first one, parallel ray, bam, hits the mirror at that point right there, reflects this time through F. Second ray is through F, hits the mirror, comes off parallel this time. Whoops. Make sure I get it right. There we go. Need that little guy. And then the third ray for a mirror, again, I can't really use that second one unless I want to measure angles, is any ray that goes through the center of curvature, and I almost miss, and that's okay if you have a ray that's going to miss the mirror, we can always just extend it to where it kind of theoretically would be. I'm almost on the mirror. It's going to bounce straight back on the same line, and you can see all three of my rays converge, and what do you know? I get the exact same properties for a mirror when the object is beyond the center of curvature as I do for a lens. They're very, very similar, just it's the bouncing rays back instead of passing them through. So I get reduced, real, inverted between F and C as my properties. So you've got a bunch. The repetition of doing all the lenses and mirror locations should start to kind of clue you in about making predictions about where the images should be and their properties. So then the next video, final part 3, will focus on diverging lenses and mirrors, and then as well as the equation, there's a lens and mirror equation that does the same thing.